Thanks, Tim.
Hello again, everyone. This morning we're going to have Max Hallgren continue his talk on the tensor maximum principle. Thanks for joining us, Max.
Thank you, Tim. So today the outline is we're first going to give kind of a bit more of a down-to-earth version of the tensor maximum principle. And that's really going to be sufficient for our applications to Ricci flow and 3 manifolds. So we're going to first prove a simple version of this in the case where our vector bundle is trivial. And then we'll prove the more general tensor maximum principle, but this proof will not really be significantly more. It won't be much more than the first case. And then we'll see some applications to preserved curvature conditions, mostly in dimension 3. And then we will finish with the Hamilton-Ivy pinching estimate, which talks about how kind of curvature tends to pinch towards positive in 3 spatial dimensions. Okay, so first let's remind ourselves what the tensor maximum principle says. So in this setting, we have a closed Riemannian manifold, and then we just have some vector field just on some Euclidean space, and a convex set in the same Euclidean space. And this convex set is preserved by the vector field in the sense that any integral curve of the ODE of the flow of the vector field, which starts in the convex set, stays in that convex set. And then the last piece of information is that we want a solution of a heat type equation where the reaction term is this vector field. Okay. All right. So this is in the case where the vector bundle. This is the statement of the tensor maximum principle in the case when the vector bundle is just your manifold times RK. Okay, and this was originally proved by Richard Hamilton back in 1985, and we're going to go through kind of the proof that he gave in his paper. Okay, so kind of just an example of a K and phi for which this theorem would apply is if K is just the closed unit ball in RK, and phi of u is just kind of the inwards pointing kind of radial vector field. And so in that case, we see that integral curves starting in the ball are going to just move towards the center of the ball. And a non-example would be if instead you consider the vector field, which is pointing out radially. So in that case, K will not preserve, solutions of the corresponding ODE that start in K may leave K. Okay. Okay, so for the proof, I just want to start out with this kind of elementary analysis lemma, which says that if you have a function g of 2 variables, which we can assume is smooth, and then if we have some compact set of some RK, then if we consider this spatial maximum function, so where we think of the first variable as being time, and we take the supremum of g over this compact set, then now this spatial maximum function is locally Lipschitz, and wherever its derivative exists, which is almost everywhere, we know that the derivative is less than or equal to this quantity. So this means we take the supremum over all y in the set k star of t. So k star of t here is the set of points in y where the spatial maximum of g at time t is achieved. So an example of this, okay, let me first finish the statement and then give an example. Okay, so yeah, the derivative of the spatial maximum is at most the partial derivative of g at any point where this spatial maximum is achieved. Okay, so an example of this would be, so let's say that we have just kind of 2 points which depend on time. This is maybe not actually the best example, but maybe it's just an idea of, it can at least give us an idea of what to expect. So here, the distance between x of t and y of t is kind of the infimum over curves connecting connecting x of t and y of t. And so if we want to compute the derivative of the distance between x of t and y of t, then this is going to be less than or equal to the derivative of the length of gamma of t, ddt, where we here, so sorry, this is going to be supremum over all curves gamma, all minimizing geodesics from x of t to y of t. Okay, yeah, we'll see more examples in just a slide or two. This one maybe wasn't so clear. Okay, so the proof of this is pretty straightforward. So we fix.
Max, sorry to interrupt.
Sure.
In the statement here, it's understood that this is for almost every t. Is that right?
Yes, that's right.
Yeah. Okay.
Yeah. So in fact, you can say something a little bit stronger, which is that this holds at every time where you interpret this as being the lim sup of Forrad's different quotients, but that coincides with the derivative wherever the derivative is defined.
Yeah, cool. So that's a good point to make, I think.
Right. Yeah, definitely. Okay. So given two times T2 and T1, we choose a point in our set K. So we'll call this Y star, where the spatial maximum is achieved at time T2. And then we'll look at this difference quotient. And so this part here, we're just going to show that f of t is locally Lipschitz. Okay, and so f of t here, by definition of the set of this set, is going to be equal to just g at t2 y star. And then we know that f of t1, since it's a spatial maximum at time t1, is going to be greater than or equal to this. Okay, and so combining these two facts, we get this first inequality. And then this difference is just bounded by just essentially the C1 norm of G in some compact region of space-time times the time difference T1 minus T2. So this tells us in particular that f is going to be locally Lipschitz, and so its derivative exists almost everywhere by Rademacher's theorem. And so now let's consider a time where the derivative exists, and let's consider a sequence Tj descending to this time. And that means that we can pick these yj stars, which are going to be points where this spatial maximum is achieved. So here's where we use the compactness of our set K, or one place where we use it. We also kind of implicitly used it to get that this is finite. So we can pass to a subsequence that these points where the spatial maxima occur accumulate on some point y star. And so just by kind of passing this to the limit, we get that y star is now going to be a point where the spatial maximum of f of t is achieved. Okay, and so then this inequality kind of follows us up here. So we get that this difference quotient of the spatial maxima is bounded by by the mean value theorem by some time derivative, where here yj star is approaching y star, and these tj prime are just going to be sometimes in the interval tj and t. So in particular, they're also going to be converging to t. Okay, and here's a typo. So this should be g. Okay. Okay, so in particular, we get that this difference quotient is bounded by this. As I mentioned, y star is actually in the set k star of t. Okay, so that's pretty much all I wanted to say about this. Are there any questions? Okay. So now I want to go over one more preliminary before we start the proof, which is just something about convex sets. Okay, so let's, this is okay. Okay, so suppose we have a closed convex set of some Euclidean space. So a support function for this convex set at a point in the boundary of the convex set is a linear function, a linear functional on Rk, whose operator norm is 1. Actually, do we want the operator? No, just take the Euclidean norm to be 1. I think that's what we want. It's not too important. And Okay, and what's more is we want this linear functional to take a larger value at V than anywhere else in our convex set. So I'm gonna attempt to draw an example of this. So at any point of our convex set where the boundary is smooth, so then a support function, okay, is going to look like this. So it's going to be so this is the set alpha equals alpha V. Okay, and so this is going to be exactly the tangent space of K at our point V, let's say. And so here's going to be where alpha is greater than 0, and here's going to be where alpha is less than 0. So it turns out that at a point where the boundary is smooth, there's a unique support function, but at a point like this, you could have a support function that looks like this, or a support function that looks like this. You have infinitely many support functions here. Okay, and it's easy to show that for any, well, it's elementary to show. It takes a little bit of work to show that any convex set is the intersection of kind of all of these half spaces alpha less than 0 as we vary over all support functions for our set. And now if we restrict our attention to just support functions at a fixed point, then the intersection, actually a set that I isn't quite. Okay. So the intersection of all of these kind of half planes at a single point, that's going to be the tangent cone of our convex set K. So for example, the tangent cone, let me erase some stuff. So the tangent cone at this point is going to look something like this. Okay, so it's going to be everything in here. Yeah, and then at this other point V, the tangent cone is just going to be a half space. Okay, so we're interested in these tangent cones because that's going to basically be our way to characterize when a convex set is preserved by an ODE. Okay. Yeah. Are there any questions about any of this? Okay. Okay. So as I stated, we'd like to kind of reformulate what it means for a convex set to preserve integral curves of an ODE, and so our reformulation is going to be that. For a vector field in a convex set, any solution starting in the convex set, any integral curve of our vector field starting in this convex set remains in the convex set, if and only if at every point on the boundary of our convex set, our vector field points into the tangent cone. Okay, so let's see what this would look like in the following case, in the previous case. So if the vector field is pointing inwards like this, that's good. Similarly, if the vector field is pointing into this half space, that's good. Now, if of course we had a point here that was pointing out this way, then we see that our criterion would not apply in this case.
Hey Max, sorry to interrupt again, sure. But I might be having a senior moment here. Sure. If the size of the function is 1, doesn't that mean the function is just 1? Like, what am I missing?
Oh, so sorry. What I mean by this is that
so you mean alpha of V is 1 for all V or not?
So what I mean is that alpha here is the supremum over all V of unit length. It's the supremum.
So you do mean like an operated norm?
Yeah.
Oh, okay. I was confused by it's not the operated norm comment.
Yeah, yeah, I could have explained that better. Sorry.
That's all good. I just, yeah, thank you.
Sure. Okay. All right. So, okay, so let's see a proof of this. We're going to use this in the proof of the tensor maxima principle. Okay. So 1 implies 2 is not too difficult. So if we have a point in the boundary of our convex set, and if we have, so we're proving the contrapositive, if we have our vector field not pointing inside of the tangent cone at this point in the boundary, then that tells us, so by definition of the tangent cone, that tells us that there's going to be some support function at V, such that alpha of our vector field at V is actually positive. So that just means that it's pointing, that's just a reformulation of saying that that vector, phi of V is pointing out of the tangent cone at that point. Okay, and we know since V is in the boundary that, okay, this isn't, okay, this is just, let me explain what I mean by this. So here gamma is going to be an integral curve of phi, starting at V, let's say. Okay, so that explains this. And so if we just compute the derivative of, so alpha of gamma of t, then because alpha is linear, we can just bring the derivative inside and we just get this quantity, which we just argued was positive. So what this means is that for small t, alpha of gamma of t is going to be strictly greater than 0, which means that it's not going to be contained in our convex set. Because remember, the support function kind of achieves its maximum on the convex set at V. So if there's a point where alpha is greater than its value at alpha of V, then it can't be in our convex set. Okay, so that means that, okay, so we've shown 1 implies 2 then. And so now for the converse. So this is going to be a kind of function that comes up a lot today. Hopefully you'll be bored of it by the end. So, okay, we can just assume without loss of generality that phi is compactly supported. Yeah, it's not too difficult to reduce the general case to this, but let's just assume it for simplicity. So we're going to define S of V. So here, this is a function on Rk to be the distance to the convex set. And so it's a fact that this is equal to the supremum of this quantity, alpha of V minus W. And I'm going to draw a picture. I'm going to draw a picture for what this means in just a sec. But here we're taking the supremum over all points in the boundary and over all support functions at that point. So, so an example of this would be, let's say here's a circle, kind of. Here's a point V. And so the distance from V to the circle is going to be achieved by some point W. And there's a support function here at W. So call this alpha, such that alpha of V minus alpha of W is the distance. So yeah, in this case where our convex set is actually smooth there, we'll actually see that that this is going to be perpendicular to the set alpha equals 0. Okay. Okay, so this is a really important reformulation of distance to a convex set, because now you know, this distance function is not in general going to be smooth, but we have found that it's equal to the supremum of a bunch of smooth functions of V, right? Even linear functions, well, affine functions of V. Okay, and this is going to be useful in combination with our previous something that we talked about earlier, which is kind of the way that we take the derivative of spatial maximum functions. Okay. All right. So now let's apply this to, again, when gamma is an integral curve of our vector field. And so applying that lemma that I just pointed to, that we started with, we see that the so at any time t where this function is smooth, where it's differentiable rather, we see that its derivative is going to be given by, so the derivative of this, well, where we replace V with gamma of t. So maybe let me just include that intermediate step. So this is ddt of alpha of gamma of t minus W. Okay, where here so W and alpha are going to be points in the boundary and support functions at this point where the maximum is achieved. So in other words, where S of V equals this. Okay, so we see that that our spatial derivative is just equal to alpha of our vector field at the point gamma of t. Okay, so wherever this function is differentiable. Okay, so that means that we can then come. Okay, so the next step is to estimate this. So we know that alpha of gamma t, we can rewrite this as we can just add and subtract alpha of phi at w. So just to be clear, when I write phi of x, this is just a compact notation for our vector field, taking our vector field's value at point x. Okay, so we've separated this into these two pieces, and so why does this help? So we know that this is going to be less than or equal to 0. No, sorry. We know this is going to be less than or equal to 0 because well, okay, this is by our assumption that phi of v is always pointing into our tangent cone. So that tells us that this is 0 because it's exactly alpha. It's alpha of kind of a vector like this pointing into our tangent cone at our point. So okay, so this is less than or equal to 0 by our assumption. And then here we know that phi is a smooth vector field. The norm of alpha is 1, and so this we can just kind of roughly bound as some constant times the distance between gamma of t and w. But this is equal to, so this distance is the same as the distance from gamma of t to our convex set, kind of by our definition of w. So combining this and this gives you can rewrite that as this differential inequality. And since this function is in the parentheses is Lipschitz, we can integrate this. We have the fundamental theorem of calculus. And the fact that our integral curve started in our convex set means that S of 0 is less than or equal to 0. And so we get that S of t is less than or equal to 0 for all positive time, which means that our integral curve stays in our convex set. Okay, and so our proof of the tensor maximum principle is going to be quite similar actually to this proof. Okay, so the main difference is, oh, sorry, I forgot to ask, are there any questions about this slide or about the proof?
Okay. Sorry, Max, could I ask, so do you need alpha of phi of w to be strictly less than 0? I mean, do you need your field to?
Oh, no, so in fact, for this weak maximum principle, we don't need our vector field to point strictly inside of our convex set. Right. Yeah. So the strong maximum principle, which I'm not going to have time to talk about today, that says something about the case where you actually have where your vector field is pointing strictly into the interior of the tangent cone.
Right. Thank you.
Sure. Okay. So all right. So now we're going to prove the weak maximum principle in the case where our vector bundle is trivial of rank k. Okay, so in this case, we're going to consider a very similar function, S of t, to the one that we considered in the previous slide. But the main difference is now that we're taking the supremum over points in our compact manifold. Okay, and so we get a very similar expression here. Okay, and so once again, we can use our formula for the derivative of the spatial maximum, and we get that S prime of t is going to be equal to this, where now x is a point where this supremum is achieved, w is the point where this supremum is achieved, and alpha is a support function where this supremum is achieved. Okay. So yeah, so so S of t is actually just going to equal this expression. So that's, again, because the pair, or the triple x w alpha is kind of in our spatially maximizing set. And so now it remains to just estimate this. We want to estimate this similarly to the previous slide. So how we estimate this is going to be almost identical. So the main difference is that we need to find a way to estimate this. Okay, but in order to do that, we just note that alpha of u of yt achieves its maximum at x because we chose x to be a spatial maximum. And so that means that, in particular, just by the usual maximum principle or the second derivative test, this so the Laplacian of this expression has to be non-positive. But this is just a linear function, and so it's easy to show that we can bring the derivative inside and get this. So in other words, we've shown that this is less than or equal to 0. And we've also used, so we can still use the smoothness of our vector field and get kind of this Lipschitz estimate. Sorry, here I've got another small typo, so this should be alpha. Okay, and so alpha of phi of w is less than or equal to 0 for the same reason as before. And so we once again get this differential inequality, which we can rearrange to get that S of t has to be less than or equal to 0 for all time. Okay, so that's the weak maximum principle in the case of trivial bundles. Are there any questions? Okay, so this is mostly following the exposition in Hamilton's original proof, where basically, the idea is to kind of like consider first this this ODE case and just kind of add one layer of complexity each time. So the final layer is when we have here in this case a time-dependent Riemannian manifold, which in our cases will be a Ricci flow. And we're going to consider this data. So we have a vector bundle over a manifold, along with a basically a smoothly varying inner product on each fiber. So a bundle metric, which we'll call H. And then we have a one parameter family of metric connections. So that just means that each of these connections is, so it's a connection on E, and they're all compatible with H in the sense that this connection applied to H equals 0. And so in practice, these are going to kind of be obtained from, they're essentially going to be obtained from a Ricci flow, but kind of, this is after applying Uhlenbeck's trick, which I'm going to talk about. I'm going to talk about in the next section. And then we have some kind of fiber-wise convex subset of our vector bundle. So in other words, its restriction to each fiber is just a convex set of that vector space. And it's going to be closed and also closed under parallel transport, which recall means that if you start with a vector in K at some point and you parallel translate it to get a vector at a different point over a different fiber, then that is still going to be in K. And you'll see where that is going to come up in the proof. Okay, and so here phi is a vector field on E, which is tangent to the fibers of E. So really, you can just think of this as being for each fiber, you have a vector field on that fiber just as a vector space. So it's kind of like over each point on our manifold, we're in the setting of the previous slides. And then you just ask that in each of these fibers, your convex set is preserved by the flow of this vector field. Okay. So the fact that it's a vertical vector field means that its flow is going to stay in each fiber. Okay. So yeah, last week I was talking a little bit about the time dependent version of this, but it's not super important for the purposes, I think, of this seminar, and it's just a little bit more complicated. I'll say a word after I show you the proof of kind of the extra technicality that comes up in the time dependent case.
Hey Max, do you want to just clarify where the time independence is here? Because I think the H can depend on D, right?
Yes, that's a good point. So what I mean is that
Is
we
it the
don't have
K?
K of 2.
Yeah, the K. Yeah.
Sorry.
All good. Just
That wasn't clear.
there's a lot of time everywhere, so it's like
Yeah, right.
what
Yeah,
exactly does not
yeah,
depend on
this
D?
time, that time.
Yeah.
Yeah.
Okay, it's the K.
Yeah.
Got it. Yeah, sure.
Right. Okay. So okay, so this was again proved in Hamilton's paper, and so he just says that if you have, oops, I forgot to write down that you have a solution Laplace u plus b of u. So here u is going to be a section of this vector bundle. You think of it as a time varying section, or one parameter family of sections. So if a solution of this equation kind of starts in your convex set, then it will stay in your convex set for all future time. Okay, so the differences here versus the case of the trivial bundle is that is basically just formalism. it's not much more than that. And we'll see that in the proof. The proof is about the same as well.
Sorry, Max.
Okay.
Could I ask a quick question? Where do you need the metric on your manifold? Doesn't seem to.
So in order to make sense of this Laplacian.
Oh yeah.
Yeah. Is that the only place? Yeah, maybe that's the only place where it comes up.
So it's right. Yeah. So you have.
Yeah. So maybe I should say. Oh, sorry. Go ahead.
Yeah. So you have the metric on the tangent bundle, and separately have this metric H on your other vector bundle, right?
Right.
Yeah.
Yeah. So what I mean by this Laplacian is it's actually nabla of t squared, and then we take the trace with respect to g sub t.
Right. Yeah.
Okay. Okay. So yeah, the proof of this is actually quite similar to in the trivial bundle. So the main differences are, so first of all, here when we're defining this function s again, so this set is going to depend on x, right? Because we're no longer thinking of our convex set as being in a fixed vector space, but rather we have like a one parameter family of vector spaces and of these k, not a one parameter family. We have a collection of vector spaces and these corresponding k sub x. Okay, but we have a similar formula for what the derivative of this thing is in time. So we get this once again. And just by the exact same argument here, we can estimate this by c s of t. Right. So this is again using the fact that our convex sets are preserved by the ODE. So that's how we estimate this term. And then to estimate this term, that's where we're going to use the fact that our convex set is closed under parallel translation, because how we actually, we want to show that this is less than or equal to 0. And in order to do this, we're going to extend this this function alpha to a section of the dual bundle of E star. So I'll kind of maybe draw a picture of what's happening. So here we have our point X where the minimum is achieved. We have a bunch of radial geodesics pointing outwards. Okay, and so we're going to extend alpha by just so alpha, remember, alpha is in the dual space over the fiber at X, and we're just going to extend this so that it's actually a section of E star in some neighborhood around X. Okay. So yeah, that's how we define alpha, because we want alpha to be defined everywhere and not just at X. Otherwise, it doesn't really make sense to talk about the Laplacian of alpha of u of xt, which is what we want to do. Okay, and similarly, we're going to choose. So we just choose an orthonormal basis at a point at the tangent space at a point X. And we also parallel translate these along the radial geodesics. Okay, and when we do that, we can now so use the fact that once again, just by the second derivative test, we know that the Laplacian of alpha of u is going to be less than or equal to 0 because it achieves a local maximum at x. And now we want to be able to relate this to this. And so in order to do that, so we kind of expand things out. So here there would normally be an extra term that would have something like nabla ei. But here we're just evaluating at x comma t. And so this is going to vanish because we decided to parallel translate ei. So just kind of by construction of this local orthonormal frame ei, this is going to be 0. And so now, so when our connection, so far this is actually just the directional derivative in the direction of ei. But when this hits this term, right, so we get our connection applied to alpha and our connection applied to u. And then we still have another derivative, which we're taking. Okay, and so what happens here is we get a second derivative. Okay, I'll deal with that term last. So ei differentiates alpha, but we parallel translated alpha along radial geodesics. So in particular, we know that nabla ei alpha is 0 at x. Okay, and then let's see, we also have the derivative falling on here, but that term vanishes for the same reason because this vanishes at x. And then so lastly we have oh yeah, is there a question? Oh, sorry. Okay, and then so we have the second derivative falling on alpha here. And the reason that that is 0 is because so this is not only vanishes at the point x, but it actually vanishes along the radial geodesic in the ei direction. Okay, so this vanishes uniformly along the geodesic in the ei direction, which means that its covariant derivative along this direction has to be 0. Okay, so this is 0, and then when the derivative hits this is 0, and so all that's left is when this derivative hits this, and then when we sum, we just get this term. Okay, so this is just a computation, but
Max,
this is, yeah, sure.
I'm confused by that very last bit. So for every ei, the alpha vanishes along the ei?
Right.
Well, the gradient of alpha. Yeah. No, I'm okay. Yeah. Okay. Sorry, I confused myself. I got. Sure, yeah.
No, I appreciate all the questions. This is helpful. yeah.
Thanks.
Okay. I know people are following. So. Okay. So all right. So now we've shown that this is less than or equal to 0, and so once again we get s prime of t is less than or equal to c s of t. Okay, and so as before, this concludes the proof. And so there's a couple extra technicalities that come up in the case where k is varying by time. So for example, kind of one place where you have to do a little bit more work is kind of in the characterization of when a convex set is preserved by an ODE. So instead of considering like the tangent cone at a fixed point, you have to consider kind of a time-dependent kind of analog where you kind of look at these like forward-pointing tangent vectors. It's just more work, but you can. So a good reference for this is Ben Chow and Lei Ni's book, Ricci Flow Techniques and Applications, in the second volume. I'll have the references listed at the end. Okay, are there any questions about this before we go on to the next section? Okay, so yeah, the proof isn't that much different than the trivial bundle case. Okay, so I think so far you guys have talked about Uhlenbeck's trick, but I think I haven't seen all the videos, so please someone correct me if I'm wrong, but I think you've talked about it kind of in a sense of this Uhlenbeck connection on on the spatial tangent bundle of a space-time. Okay, so now I want to introduce the kind of a different way of thinking about Uhlenbeck's trick, which I think was what was originally called Uhlenbeck's trick, because I think Hamilton just mentioned in his paper that he learned it from Karen Uhlenbeck. So suppose, okay, so let's just suppose that we have a Ricci flow now in a closed manifold. And so let's just fix a bundle isometry at time 0. So all we're doing here is we're really just relabeling our tangent bundle and our metric. And it kind of, it'll make more sense why we're doing that in a minute. But so we start with this, which we can really just take to be the identity map at time 0. Okay, and we're going to define a 1-parameter family of bundle isomorphisms. So that just means that it's a map between two vector bundles that, when restricted to each fiber, is a linear isomorphism. And so we're going to define this by just solving this ODE essentially in each fiber. So the time derivative of iota applied to a vector v. So this is going to be now, so v is going to live in E. It's going to be a vector in E, is the Ricci curvature of iota t of v. Okay, does this make sense? Okay, I think so. Yeah. Okay. So yeah. So basically, what's happening is in each. So I don't know if I can draw this. So we have two vector bundles. Over each fiber, we have a linear map from one fiber, a fiber in one vector bundle to a fiber in another vector bundle, and we just kind of evolve this over time according to this thing, this Ricci curvature, which we're viewing as taking in a vector and spitting out a vector. Okay, so we can just think about this when you restrict to a fiber as just being an endomorphism of some vector space. And the reason we do this is because of this really nice fact, which is that if you now look at these bundle isomorphisms, then these are actually going to be bundle isometries. So which means that they kind of, so it preserves the metric, even though notice that this GT is different from what we started with.
Sorry,
yeah,
sorry, Max. So on the right-hand side, you compute Ricci relative to G0, right?
Sorry, so this is going to be G sub T.
G sub, right.
Okay. So maybe just a more down-to-earth way of saying this first fact is it's essentially equivalent to the fact that if you have an orthonormal frame of your fixed vector bundle, and you look at the image under this bundle isomorphism, so this gives you a local frame of the tangent bundle, but in fact it's going to be an orthonormal frame. So that's the content of this fact, and pretty much of this fact as well. Okay, and so anytime you have a map between linear spaces, you have a map between tensor products of those linear spaces, which is induced. And so it's pretty straightforward to show that this map iota of t is also going to be a bundle isometry between these tensor bundles, where you have the induced metrics from H and from G sub t. Okay, and so the way that this is related to the version of Uhlenbeck's trick that you've all seen is that if we take a tensor, a time-dependent tensor, let's say, on our bundle E, and if we take just the normal time derivative and then apply our bundle isometry, then this is the same as if, oops. This is the same as if we apply our bundle isometry and then differentiate, where this is now Uhlenbeck's connection in the direction of our spatial time derivative. So kind of this Uhlenbeck trick is kind of a way of just seeing this Uhlenbeck connection as just being kind of, at least in the time direction, as just being a fixed time derivative of a fixed vector bundle. And notice that now, since we're going to be considering a fixed vector bundle, and we have a fixed metric on this vector bundle, Now we're going to be in the setting where we can apply the tensor maximum principle as it was stated in the previous slides. Okay. Are there any questions about this? I'm going to give a. No, I'm not going to give a proof of this one, but it'll be. Hopefully, the slides will be posted on the website or something. But the proof isn't too difficult. Okay, so the important corollary of this fact that I stated is that so we had this formula for the evolution of the curvature tensor under Ricci flow with respect to Uhlenbeck's connection. And so what that translates to is now if we consider these, where now these are all going to be tensors on our fixed vector bundle E. And this is just the usual time derivative. And this is now something where we can directly apply the tensor maximum principle. Yeah. So we can apply the tensor maximum principle with this as our vector field. Okay. Are there any questions about this? Okay. So let's see a quick application of this. So we're going to see that non-negative Ricci curvature is preserved in 3 dimensions. So I think that you guys briefly talked about this evolution equation for the Ricci curvature. So here, this is the Riemannian curvature acting on symmetric T tensors. If you do that, you can write out in coordinates. Yep.
Can I ask a quick question?
Sure.
Perhaps you don't know the answer to this one, but do you know why do they call this E and not TM?
Oh wait, sorry. Say that one more time.
Well, you just presented this abstract vector bundle over M, which is actually isomorphic to the tangent bundle, right? You only put like a fixed metric. So do you know what the reason why we call it E and not just TM?
So I'm not sure if this is the reason, but it kind of helps for me to kind of remember that I'm considering tensors on this bundle after I've kind of pulled back by these iota of T using Uhlenbeck's trick. So it's kind of a way of reminding yourself that you're not working with the tensor field on TM so much. You're kind of looking at the tensor field after you move it using iota of T.
Okay, but the only thing changing is really the metric, right?
So in a sense that
yes.
So the bundle metric isn't changing, but oh, you're saying over here, yeah. So the only thing changing here is right.
So you're moving the frame to keep it orthonormal, essentially.
Yeah,
right.
exactly. So this is really the same as solving that ODE for orthonormal frames.
Right. Okay. Right. Thanks.
Sure. Okay. So yeah, the evolution equation for Ricci curvature is given by this. And so in any dimension, we have a decomposition of the curvature tensor into kind of these, invariant pieces with respect to the ON action on tensors. And so in 3 dimensions, this looks pretty simple. And so using this, we can actually rewrite this equation in terms of just the Ricci curvature. So there's nowhere here that the full curvature tensor appears. And so now we'd like to apply the tensor maximum principle to this. So we're going to take, in this case, E is going to correspond to our vector bundle now of symmetric 2 tensors on M, and our convex set is going to be the symmetric 2 tensors, which are just non-negative at each point. Okay, so on the boundary of this convex set at any fiber, right? So when can a 2 tensor be on the boundary of the set? That means that one of its eigenvalues has to be 0. So in particular, the Ricci curvature would have to, any tensor on the boundary of this has to have rank at most 2. And so that means that we have this Cauchy-Schwarz inequality. Normally we need a 3 in the denominator. And yeah, we similarly get this, where this is, so just a scalar curvature times the metric. And so the upshot of this is that now this is greater than or equal to 0. These 2 terms combine to be greater than or equal to 0. And we get that non-negative Ricci curvature is preserved in 3 dimensions. And also you can show that non-negative scalar curvature is preserved. Okay, but this basically follows from some linear algebra and the fact that positive curvature operator. Okay, so I'm going to skip this part and maybe Tim can present on that next week. Okay, so the last thing I want to talk about is this Hamilton-IV pinching estimate. So here we're going to let lambda 1, lambda 2, and lambda 3 be the eigenvalues of the curvature operator. So as an operator as a symmetric operator on two forms. Sorry, on the wedge, well, on this space. Okay, and so we're going to consider this function, which increases just a little bit faster than x, right? So it's going to be convex and increasing. So it's easy to show that its inverse is going to be concave and increasing. Okay, and so with this, we can now state Hamilton-IV pinching. So this is a little bit different from the version that's usually stated in the literature, because this doesn't have time explicitly appearing here. But this is really sufficient for kind of most applications to at least Ricci flow in 3 dimensions, if you're just interested in finite time singularities. Okay, rather than like long-term behavior of solutions which exist for all positive time. Okay, so if you have a closed Ricci flow, then after rescaling your initial metric, otherwise you just get a couple like extra coefficients in here. So don't worry too much about what this means. We have that the scalar curvature has to be at least -0.5, and our lowest eigenvalue of the curvature operator plus F inverse of the scalar curvature has to be greater than or equal to 0. Okay, so what does this mean? So it means that if the lowest eigenvalue of our curvature operator somewhere is less than or equal to -1, then not only is the scalar curvature greater than or equal to lambda 1, but it's actually greater than or equal to this function, which blows up much faster. I mean, not much faster, slightly faster than x. So in other words, if there's a negative eigenvalue, an eigenvalue of the curvature tensor less than or equal to -1, then the scalar curvature must be even larger, which means that so what this says is that basically if lambda 1 is less than or equal to -1, then lambda 3. So the largest eigenvalue of the curvature operator is going to be much larger than the absolute value of lambda 1. Okay, and so when you guys eventually learn about kind of Cheeger-Gromov's compactness theorem and singularity models, then this is going to translate to the fact that in 3 dimensions, kind of singularities, if you kind of zoom in and extract some kind of limit, the limit is going to have non-negative curvature. So that's really a consequence of Hamilton-IV pinching. Okay, and so the proof of this is as follows. So remember, Hamilton's ODE is that corresponds to the vector field on curvature tensors, which is takes in a curvature tensor and it spits out the curvature tensor squared plus this thing called the Lie algebra square of the curvature tensor. And so now if we consider a curvature tensor and we just diagonalize it, lambda 2 and a 3, then so these first terms are going to correspond to R squared. These terms are going to correspond to the Lie algebra squares. And so that means that if we can show that solutions of this system of ODEs preserve the inequalities, so these 2 inequalities, which appeared in the statement of Hamilton-IV pinching, then so if these inequalities initially hold for a solution of this, then they continue to hold. So that's all we have to show. And also we have to show that the set of curvature tensors satisfying these conditions is convex. The other conditions are easier to verify. And so let's first think about why the set is convex. So this subset is going to be everything to the right of this red line and everything under this blue line. So it's pretty easy to see here it's convex. And then in order to relate this, so this is just here, I should say, on this axis, we have the scalar curvature, and on this axis, we have kind of the negative part of the lowest eigenvalue. And so basically, if we have if we have a curvature tensor whose scalar curvature and first eigenvalue is here, so this corresponds to R1, and here which corresponds to R2, then because the scalar curvature is just the trace, it's going to be linear. So if we look at kind of where lambda 1 and R corresponding to this convex combination of these curvature tensors lands, we know that the trace is going to lie in between the traces of R1 and R2. And so it's pretty easy to show that lambda 1 is actually concave. So minus lambda 1 is convex. So that means that kind of lambda 1 is going to lie somewhere above here. So we have this line, and then kind of the point corresponding to TR1 plus 1 minus TR2 lies kind of above this line in the R direction. Wait, sorry, did I say that right? No. It's going to lie down here. Somewhere down here. Okay, because, yeah. All right. Okay, anyways, this is super important. Okay, so, I mean, it's not super difficult to show. It is important. So the slightly trickier thing is just showing that that Hamilton's ODE preserves this convex set. And so one of these isn't too difficult. If we just write out the ODE, so if we write down the derivative for essentially the scalar curvature, this is actually going to be greater than or equal to 0. So it's easy to check that that this is preserved by our ODEs. So now we need to check that this is also preserved by our ODEs. And so to do that, remember, we just need to make sure that at the boundary, kind of our vector field is pointing into the tangent cone at that point of the boundary. And so this just translates to assume that you have some curvature tensor where you actually have equality here. So that means that you're on the boundary of this convex cone. Okay, so in particular, since this takes values from -1 to infinity, this tells you that it takes values from 1 to infinity. That tells you that lambda has to be less than -1. So some algebra tells you that the sum of lambda 2 and lambda 3 have to be greater than 0, and in particular lambda 3 has to be greater than or equal to 0. So now we want to show that this this greater than or equal to 0 is preserved, and so let's just differentiate this whole thing in time. So when we differentiate this piece, we can just use the formula for derivative of an inverse, and we get something that looks like this. Yeah, don't worry too much about the computations. I mean, you can. It's something that. Yeah, I'll post the slides. Hopefully. Okay, so now if we add in this extra term, we do some algebraic manipulations, we just get that this is greater than or equal to 0. So I kind of ran out of time. Okay. Yeah, are there any questions about this last part? So basically we reduced Hamilton-Ivy, this Hamilton-Ivy pinching to showing that we have this convex set and showing that this, and then just kind of ODE analysis. Yeah. So, okay, that's the basic idea. Yeah, so usually the other version of Hamilton-Ivy has some kind of term that kind of shows that as t goes off to infinity, then your sectional curvature is actually going to be almost non-negative. But this version is kind of enough for studying finite time singularities. Yeah. Oh, and references. Oh, sorry.
Cool. Let's thank Max for another good talk. Any concluding remarks or questions for Max? No one has any questions on the pinching estimates? Okay, well, I guess I'll stop recording, but before I do that, let's thank Max again for another good talk. All right, thanks everyone for coming. Hopefully we'll see you next time.